Section 11. The Standard Cosmological Model, Lambda CDM. Friedmann's equations can be solved for the expansion scale factor A of t once we know the composition of the universe, which we will cover now. The present energy densities of radiation, matter, and dark energy, and the equation of state parameter W for dark energy, and the curvature parameters kappa and r sub 0. Then cosmologists know the energy densities, pressures, and temperature at any time in the universe's history, and can apply physics to determine what is happening to matter and energy at each time. Cosmologists use multiple astronomical experimental techniques to try to determine the present composition of the universe, none of which can be measured in a lab on Earth. No single technique gives a narrow answer, but the different techniques overlap in a way that narrows the most probable range of values, which is called concordance. This does not mean all cosmologists agree on each value. It is not universal consensus. Cosmologists work to improve the values. Cosmologists' current standard cosmological model is also called the benchmark model, concordance cosmology, or Lambda CDM, where capital lambda denotes constant dark energy density, the cosmological constant, W equals -1, and CDM denotes cold dark matter. Models where dark energy density can vary with scale factor are called WCDM. Supporting the standard model, it is believed that our observable universe has zero curvature, flat Euclidean space, kappa equals 0, or that the curvature term has been insignificant thus far. The sum of the energy densities equals the critical energy density for a flat universe, presently and at all times. It is believed that the dark energy density is constant, the cosmological constant, W equals -1, or that any change has been inconsequential so far, though it may be important in the next hundreds of billions of years. All of my graphs and calculations assume zero curvature, and almost all assume constant dark energy density. According to the standard cosmological model, the total energy density of the universe equals the critical energy density for flatness, which is presently 4,829 million electron volts of energy per cubic meter. A single proton has rest mass energy of 938 million electron volts. So the energy density of the universe is equivalent to 5.1 proton rest mass equivalents of energy per cubic meter. This is quite small, about a millionth the energy density of the Milky Way galaxy, and much smaller than the best vacuum created in a lab or the vacuum of interstellar space. The critical energy density is about 65% of the average matter energy density of our local group of galaxies, which contains the Milky Way, Andromeda, and 30 smaller galaxies, and a lot of intergalactic space. Much of the volume of the universe, the huge cosmic voids with no galaxy superclusters within them, presumably has energy density equal to or slightly less than the critical energy density. In other words, the universe is a pretty good vacuum, but we live in a tiny overdensity lump, and our telescopes see light from other distant, tiny overdensity lumps. Presently, 69% of the energy of the universe is dark energy. 31% is matter rest mass energy. And less than 0.01% is radiation energy. I believe that the dark energy density is presently around 45% of the average matter energy density of our local group of galaxies. Now we know how each energy density component changes with the scale factor, and we know the present energy densities. We can easily calculate the scale factors at which each energy density component loses its dominance to another component. Radiation dominated the expansion of the universe for the first 50,000 years after the Big Bang, actually starting a very small fraction of a second after the Big Bang, as we will learn later. Then the scale factor became large enough that radiation fell below matter, and matter dominated the expansion of the universe for the next 10.2 billion years. 3.6 billion years ago, the scale factor became large enough that matter's energy density fell below dark energy, and dark energy has dominated the expansion of the universe since then. Expansion is becoming exponential with time, and scale factor will increase by a factor of 10 every 40 billion years. This is an important change for the universe's future.